All right, let's get started. So just thank you to those who have been messaging me about the My Open Math. Again, that's just like a side project that, it's really sponsored by the state of Oregon, and that's why I'm like kind of doing this big lift. So I really appreciate it. And then yeah, if you didn't like complete the homework completely on the My Open stuff, like that's fine. I'll still give you credit for doing it, trying it. I know there's bugs. Just send me the bugs and send me a screenshot, right? Like I need a screenshot of what your input is or what's going on, so I can debug it properly. And then yeah, just a pro tip. I don't know if any of y'all have been playing with AIs, but I found that Grok was very helpful for coding. Like I was wasting way too much time with the Copilot, and which is I think basically ChatGPT, but RCC. Now I'm like telling you way too much, but RCC pays for the Microsoft Copilot, so I was trying to use that, and it was horrendous. But Grok got me going, so I hope that each week I'll be a little faster. So I know I haven't posted anything yet with the My Open Math, but I'll get that going. And like I said, hopefully I'll be faster now that Grok is helping me and is a lot more accurate. And then I apologize, I haven't like graded things by hand yet. I don't know where the weekend went, but I'll catch up. I know somebody was asking me about homework, so I think I have it. Like I said, I'll probably have some time after class to do all the reconciling. So I haven't transferred over the My Open Math grades either for quizzes. So I'm a little behind on grading. I'll admit that. So yeah, I'm teaching a heavy load. There are like 70 of y'all at least in my CHEM 104 classes combined or something like that. Plus I teach another 30 in my 200 levels. So yeah, a lot of grading, but I will catch up. Any other kind of questions, comments, concerns? Yeah. Yeah, yeah. Well, ideally, if you're in person, you do the in-person quiz, but I think people were already like absent or something, so that's why I opened it. But yeah, if that's why that's part of why I'm redesigning it on My Open Math, because then Blackboard starts like making too many columns. But I can fix all that in the end. But that being said, your Blackboard grade usually is not accurate. So this is always an issue. But like I said, my goal is like not to give people bad grades in this class. It's a 100 level science. Most people get an A, maybe get a B, but just kind of do the best you can, and I'm sure the grades will work out. Geez. Oh, other important. So if you're in person, we have the flame test lab this week. So wear cotton clothes for flame reasons, and then also wear, of course, your pants and shoes. Right, I don't want to see any shorts this week. We are working with 6-molar acid, so you definitely don't want to obviously put that directly on your skin. All right, other questions, comments, logistics? All right, so let's go over some things. Oh, something I did want to mention. Somebody brought it up last week with the quiz. I somehow forgot to talk about the diatomics. I don't know, I got so excited about allotropes that I forgot to mention our diatomic elements. So I was probably going to throw that out for the in-person people if people got that question wrong. But let's go over the diatomics since I totally skipped that on like week 1. So we have these diatomics, and so this just means that these are elements that are paired with itself in the elemental form. Meaning, right, you find them in nature as their pure substance, again, as a diatomic. And so on your periodic table, I would highlight the 7 diatomics. So you have hydrogen, that's kind of a little oddity over here. And then the rest make this little 7, which helps you remember that there are 1, 2, 3, 4, 5, 6, 7 diatomics in total. And then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine there. So just highlight those. And again, going back to our classifying substances, when I should have presented this information, right, they would still be an element, even though there are two of them, which I think you all got from the allotrope discussion, but I'm writing it out, but I'll scroll back up. So this is it in written out form, and I'll show our periodic table. So again, I highlighted it, which I think is the easiest form. So you have hydrogen in that corner, then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And then that's rewritten down here. And so again, and we'll get a feel for it as we kind of progress. But as we do a reaction, like, oh, let's react nitrogen and hydrogen. Well, when you do that, you know that you have to put a little 2, right? So as soon as you say, well, nitrogen plus hydrogen, and then this makes ammonia. But, right, you have to start as a diatomic. And then now we get into balancing. Yay. But that's kind of where we're going. So we want to write our diatomics properly. All right, let's continue with electron configuration, because like I said, we want to understand this. I know we left off, and then this will help us continue with chapter 3 and kind of putting all these reactivity things together. And we'll also go over our periodic trends after this. So we'll see if we start chapter 3 formally, but it's fine. We're kind of dipping in both right now. This is going to help us. So let's see. So we left off, we were basically kind of finishing off our neon. So let's just kind of recap. Again, you always start at the beginning, right? So this is our first level. So 1s1, 1s2. We start our second level, 2s1. And again, looking back, okay, just reminding ourselves that this first group here, our alkali metals, all have 1 valence electron, right? There's a little 1 here. So again, make sure that's annotated on your periodic table. So okay, now we're at 2s1, 2s2 for our valence 1. Then we started right to P with our P block. And then again, you can have this labeled up here. So NP1, NP2, NP3, NP4, NP5, NP6, right? So that was our noble gas configuration. Let's see where we left off. I think we did neon. I'm just trying to remind. Yeah, so we left off on neon. Good. And so let's just practice. Let's do magnesium for a second. So see if you can write the electron configuration for magnesium. You could use the shorthand, right? Do you remember what we talked about, the shorthand noble gas? You could always write out the full shebang. So what do we get for magnesium's electron configuration? And you can give it to me in any form. Yeah. Excellent. Is this what we all got? And then did anybody write it in the abbreviated form? Yeah, what'd you get, James? Oh, you can always look back. So we do have a periodic table in the room. I'm gonna have an extra floating. Oh, yeah. Let me see if I can find an extra of it. So did anybody get our uh, our abbreviated electron configuration then? Perfect. So yeah, I think I need to make a few copies. I was trying to get like a non-pink one. But perfect. So went straight back to our previous noble gas, 3s2. Good. And then again, just like recap, sanity check, we can look at P table too. And so notice, especially when you're practicing at home, so we can click on our magnesium here. Well, go up to electrons, so click on electrons, click on magnesium, and then right there's the electron configuration. Again, I apologize, I can't zoom in a little more. It also has the abbreviated form, so neon 3s2. So that looks good. Excellent. All right, so let's continue. So 3s1, 3s2. So now we're still at 3p. Let's just do chlorine for a spot check. So see if we can do chlorine's electron configuration. So do we have chlorine already? Oh, we skip. So don't skip your 2p6. Yeah, so 2p6. Then what comes after next? So you had the 3. Well, before 3p5, what do we need to fill up? Hint, hint. Yeah, 3s2, right? So don't skip anything. So that was good you had the ending. But again, just to emphasize, oh, where's my periodic table? So right, you always start from the beginning. So we have to fill in, right, every electron. So the 1s2, 2s2, 2p6, 3s2, right? You're just following in numerical order. And then, yeah, 3p1, 2, 3, 4, 5. Excellent. And so now how many valence electrons does chlorine have? 7. Excellent, right? So you have your outermost shell. And then again, right, annotated over here. Okay, we have 7a, also reminding us, yes, we have 7 valence electrons. And then we can write our Lewis dot structure. I'll write it in this form first. So right, we fill up our S first. It doesn't matter which side you call your S side. Then we have our 3 degenerate p orbitals. Degenerate just meaning they're at the same energy level. So you fill in each one of them first. So 1, 2, 3. Now we can go back and pair 4, 5. And then I'm going to draw my Lewis dot structure to look like this. Again, doesn't matter what side's what, just as long as we have 7 dots around it in the end there. All right. So let's keep going on. So right, this finishes 3p6 here with argon. And then we have potassium, so 4s1, 4s2. Now this is where I mentioned, well, things start to get a little weird. And so we'll do a quick recap. I know we had said this earlier, but going back, if I can find it in my notes. So thinking back to kind of our simplified onion ring, right? Well, we're at the n equals 3 level, and we said, well, we have to have an s, a p, and a d orbital. And so now that's where our d comes in, because like I had mentioned, our 4s and our 3d are pretty close together. And that's something else that we should mention and kind of appreciate. This is not the best diagram for this. I'll try to find a better one. But basically what we want to show is the energy gap is the largest between the first and the second. And then for each subsequent energy level, they get closer and closer together. So that's why I call it things get weird. But it's just that electrons can kind of shift over to different energy levels based off of what is more energetically favorable. And we'll kind of see where that comes into play. So start off, which is scandium's electron configuration. So see if you can write that out. I'll give y'all a second before we go over it. And I kind of gave you a hint on here, but so what do we get for scandium? Any guesses? Yeah, you want to go, Maria? Oh, 3D1. So that's the only, yeah, because remember, we're still at the third energy level, so that's the confusing part. And then go back to here. So try to label it. So this starts again, 3D1 there. So star it, whatever. So you don't forget that we still have to go back to 3D. All right, so let's do the electron configuration. Let's do vanadium for a second to practice. And then we'll do chromium and we'll talk about oddities. So you have vanadium. So what do we get for vanadium, right? We can kind of work off of scandium. What's our electron configuration? Perfect. So that looks good. So right now everything's filling in normally. So now let's look at chromium. Oh, so remember this goes back to our noble gas configuration. So if we're looking at vanadium, sorry, you always go back to the previous noble gas. So that's why he picked argon, right? And you can look numerically. Well, we can't pick krypton, right? We're not there. So we're only at 23. So that's why I have to start at the previous noble gas. And again, the bracket just tells you, okay, electron configuration of argon. So starting with that, and again, you only can like do this trick with the noble gases. But yeah, so that's why we start at argon. So that just saves us, right, from writing 1s2, 2s2, 2p6. Like, it gets very repetitive. Yeah, I'll try to print you a copy of the periodic table during the break. I'll get some extras. All right, so try chromium. At least, like I said, what we expect, and then I'll talk about expectations for like correct answers. So what's chromium? And I'll just kind of put expected. So what do we get for chromium? What are we thinking? And so let's pause here, right? So now I'm going to say our caveat, because again, I wrote expected here. And again, we're only Gen Chem 100 level, but I do want you to at least be like aware of what we call these exceptions so that they doesn't seem like, again, kind of random patterns. And so I try not to quiz you guys on these oddities. But if it were to come up on like a quiz or an exam and I ask this question, this is a perfectly okay answer. Because, right, it's numerically correct. So, okay, and the big thing that I care about is that your electrons, your total number of electrons are good. So, want total. Now, let's look at what actually happens and kind of why. So, this goes back to what I was saying, that these energy levels are closer and closer together. And so, if we draw this out, so we have our 4s here. That's just slightly below our 1, 2, 3, 4, 5 3Ds here. And so what happens, and let's kind of draw this out, right? You have 1, 2, 1, 2, 3, 4. But here's the issue, and this is why it happens. So again, energy difference is pretty low, pretty small. But when you pair these two electrons, right, they have opposite spins. So you pay a small energy price. So I'm going to say you pay a small energy price to pair. So it's actually more favorable if you could somehow put an electron in every orbital. And so that's what happens. So then more stable actual configuration is then, that's why, so one electron is going to be removed from our 4s so that it doesn't have to be paired. And then it's going to move into that empty 3D. So this is the true electron configuration, which then, if we were writing it, would give us argon. So 4s1, 3d, 5. But like I said, I don't really expect this from y'all, or like another way that I might ask this question would be like, oh, you know, the expected electron configuration is 4s2, 3d4. Why is it actually this, right? And then you could say something like, this is actually more stable because you have to pay the energy price to pair them. So it's actually much more favorable, right, to put one in each orbital. Does that kind of make sense to people? Okay. It's okay if it doesn't, right? So like that's the whole point is like I'm not trying to bust people on this. Like this is not going to be on the exam, or if it is, like I said, it'll be in a way that is easy. So let's try to. It's pretty consistent, but let's look at a few things. So to answer your question, and so this is where the P table is really nice, because right, you can check yourself, you can test it. So chromium, and P table does have it correct, and it is in red, right? Like it's in red saying, hey, this is a funny one. And so we have, yes, it is odd of 4s1, 3d5, right? And it brings up this rule, but basically, again, all we're saying is that it requires less energy to put them in what are essentially degenerate orbitals, aka, right, the same energy level. I was trying to find, this isn't like the best picture that I had in mind for this. But going back to my other point, again, you have your biggest gap between your first and your second energy level. And then each subsequent energy level, right, they're getting smaller and smaller and smaller. So again, this sort of like weird behavior, we'll call it, becomes more prevalent as you go on. So manganese goes back to filling normally, right? So 4s2, 3d5. Iron's normal, cobalt's normal, nickel. But then notice copper, right? You have that same issue where instead of pairing at the 4s2, it rather just fill in all those Ds and pair them, which is kind of odd, right? But it rather pair them in the Ds than the S's. And you could always like write that down. But like I said, I'm not going to test you over all these like oddities, right? Like that's my point. I'm not going to be kind of busting you for that. But at least like try to appreciate it. Okay, so now let's continue. So we'll revisit oddities. So now we're at 3d10 with zinc, right? So 4s2, 3d10. And then again, mark your periodic table. So now we went from 3d10, now we're back to 4p1, right? So let's just do germanium's electron configuration for a spot check. What do you mean flipped? I guess you mean like over here? I'm not understanding the question. Like why does it start with the 1s on bottom? So it's just showing that you have to fill your 1s first, right? So your 1s is always your lowest. So going back to like, even if we're doing germanium, right, that's the first energy level you start with, the 1s1. And then you just keep filling in, right? That's why I'm always like, start at the top, because it's the same thing, right? 1s1. So it just depends like what representation, right? Because these are all your little orbitals, and they're kind of in the correct relative placement, right? It's kind of hard to tell because it's so small. But for example, right, your 4s is just below your 3d, which is what we find, right? So it's kind of showing there the relative energy levels. But again, it's all about doing the lowest ones first, right? So your 1s is your lowest, it's your core, it's that sphere at the very center. And then you have to fill in your next sphere, right? Your 2s onion shell. Then with the second energy level, you get those p orbitals and so forth, right? So what do we get for germanium then? And so you can give me abbreviated or full. So argon, but then don't skip. So then we have, I would do it in order, right? Just so you don't. What about your 4s, right? So 4s2. So don't. So yeah, argon. And right, just go in numerical order just to like sanity check yourself. So you're at argon, which is 18. Then we got to fill in 19, right? So that's 4s1, 4s2, and then the 3d10 like you had said. So you had that right. So 4s2, 3d10, and then, sorry, what was the last thing you said? 4p what? So 4p2. Good. And then, so this is where things kind of get a little funny too. So at this point, we don't really care about the D's so much, right? Once we're at like the P block. And so that's the other thing kind of about this class, right? Is like we're basically kind of skipping the transition metals. Yes, we may do a few electron configurations from the transition metals. I'll keep it light, right? Because we don't want to get into all the exceptions in this class, right? We're trying to, I understand it's 100 level. And then, so once we get back to our P block, right, we can just treat it like our other main groups. So again, we're back to 4 valence electrons, right? So we really just care about our outermost. And again, we don't want to go down the rabbit hole of transition metal bonding or yada yada yada. There's a reason why we keep it separate. So okay, 4 valence electrons, and then if I want to draw my Lewis dot structure for germanium, I would draw it like shown here. So 2 dots on one side for our s orbital, 1 on each side for our 2 p's. And then again, what's so powerful about this Lewis dot structure is that it tells us how it reacts. And so that's pretty cool about germanium is, yes, it is stable as this like weird divalent species. So you could make, it's called, well, again, now I've gotten too excited, but you can make this compound called germanium chloride, and then it's also actually stabilized by dioxane. I forgot how many. Sorry, let me double check dioxane structure. Okay, just wanted to make sure I had the carbons right. But basically it forms this little adduct, but this is a nice compound. And again, all this is to show that yes, germanium is 2 coordinate, and then these electrons go on to kind of donate and stabilize this compound. But again, that's probably too deep for this course, but I get too excited too rapidly. All right. Oh, well, you should know like the dots, so like understand this, right? And again, it can be on any side. So you will have to do electron configuration, yeah, but I'm just kind of like showing you like where it's going, right? Because like that's the beauty of this is like these little dots tell you so much information, right? They tell you how they react. They tell you the geometry. Like you can get so much information just from the periodic table and then drawing the Lewis dot structure, right? Then everything starts to kind of fall out of the reactivity, which leads us into chapter 3 there. So that's why we're like spending a lot of time on it, going over the electron configuration, so it all like builds. So yeah, so that's the other thing of chemistry, is it's cumulative by nature. So like for the exams, right, like I'm only going to test you over the content that's like relevant for each half, but like the final, for instance, will be cumulative by nature just because chemistry, right, builds, which is also why people don't like chemistry, right? So that's why I'm kind of trying to go slow in the beginning, make sure we get all the fundamentals, the valence electrons, how do you write the Lewis dot structure? Because yeah, everything is based off of this. All right, so then we're here. So 4p1, 4p2, 4p3. And so maybe we should, well, actually, let me finish the electron configuration. But then I want to go back to your point of like the Lewis dot structures, because everything should get repetitive is kind of the point. It's like, oh, based off of the row, this is what the Lewis dot structure is. This is how it's going to react. And we're going to just keep seeing that and hopefully just keep driving home that point. So, okay, so arsenic, 5 valence electrons, right? Selenium, 6. So 4p4, 4p5, 4p6. So good, now we're back at our noble gas configuration. And then, so 5s1 now with rubidium. 5s2 for strontium. This is where it gets weird again, so don't forget that we're only on the 4s for the Ds, right? So this is 3d1. Yttrium is 4d1. So star that, whatever you need to do. Zirconia, right, 4d2. 4d3, etc. So cadmium, right, is 4d10. Indium is then what? What is, look at your, what did you say? So P block, and then which number? So we are at 4, so now. Yeah, 5p1. Good, you guys are seeing the pattern, right? So 5p1, 5p2 for tin, 5p3 for antimony, 5p4 tellurium, right? We're getting to our heavy elements, 5p5, 5p6. And then I want to get to these weird parts. That's why I'm just kind of going. So 6s1, right, is cesium. So 6s1, 6s2. Okay, let's talk about this because now we have some discrepancies. So let's look at P table. And let's look at this periodic table. We'll look at that periodic table. So let's pause for a second. So now we're about to start our F block. Well, let's first look at some background information about our F block. And then you'll see what's funny. All right, so we have 7 types of F orbitals. I would never ask you to draw the pictures. I really don't know how to draw them. I can draw d orbitals poorly, but F orbitals I just treat theoretically. All we need to know is, okay, well, we have 7 of them. And just like before, so each F orbital holds 2 electrons. So now how many electrons total should we have in this F block system? 14. Excellent. Now here's the discrepancy that you will find. So looking at this periodic table that I've provided here, I would have to look at which one I handed out. How many across is this? And kind of what's the issue? So yeah, it's 15, right? So, okay, let's look at this. And so usually, and then here's what's even more confusing. Okay, so now let's look at the P table, periodic table. And so from this, how it's colored, right, the implication is that lutetium should be your D block, right? and lanthanum should be your F block. However, if you click on lanthanum and you look at the electron configuration, this electron configuration suggests that lanthanum should be your D block. So that's what I find kind of confusing. And again, I don't want to get so much into it because for whatever reason, these are better characterized as D block, but then it's like, well, that doesn't match the electron configuration. That back periodic table kind of implies it a little better. And so that's how I would mark yours. So I would basically move lanthanum over here or like whatever you need to do. But lanthanum should be 5D1. And then this is where I'm like, just fill it in order, at least what we expect, right? So we're going to do 5D1 and P table. Let's see if P table backs me up.
All clear, all clear. The building can resume normal operation. All clear, all clear. The building can resume normal operation.
Okay. Well, I was not expecting a test today. Okay. So then if we look at cerium, cerium does exactly what I'm suggesting. Again, even though, right, this feels all funky, it's like just go with it and accept it. So we fill our 5D1 first on lanthanum. Then cerium starts 4F1. So again, like star this, mark this, and maybe you want to like block these off as like, okay, this is really my F block. But like I said, be prepared to see discrepancies in whatever periodic table you're looking at. So that's why I'm like, maybe you count it before you start just diving in, or you need to recognize, okay, lanthanum is 5D1, cerium is 4F1. So let's just write out that electron configuration for cerium, just so we can practice and see, right, which is the correct noble gas. You may have to look just numerically, right, because things get kind of messy looking. So I would go numerically, so cerium is 58, and then which noble gas is before cerium? So xenon, excellent, you guys are on the ball. So then, and we can kind of do this together. So xenon, I'm looking, I can flip back over here, so xenon, now we're at 6S1, 6S2, lanthanum was 5D1, 5D1, and then cerium is 4F1. And again, just count your electrons. So xenon, I can't actually read from back there, so xenon was 54. So 54 plus 4, right, gives us 58, which is cerium, right? So again, main thing we care about is that we have 58 electrons. So yes, right? Because again, we might see oddities. You might get different answers depending how you count it. I'm going to be more lenient just as long as you have your total number of electrons correct. So let's keep looking at P table for these. Also, this question in the chat is, how do you say aluminum? And so Americans, right, say it aluminum, but I don't know if you're aware, like all of Europe says like aluminium. Anyways, I won't go into the pronunciation. I think technically the Americans are wrong. I try to have an Australian postdoc try to like explain all this to me, but anyways, this fun facts. All right, so let's keep looking at this. So 4F1, and then, okay, what do you notice about this one? So we have a weird exception, right? So this is where I don't expect y'all to get this necessarily correct, right? Just go off of what we expect. So looking at this praseodymium, hopefully I didn't butcher that one. So notice that this one skips 5D1, right? And it just starts filling up with the F block. And so again, this is one of those where I would say Again, our expected is okay, right? So again, just filling in order from what we would expect from what you've been taught. So it would be xenon, 6s2, 5d1, 4f2, right? And so again, perfectly correct answer on an exam, on a homework. Again, I'm going to try to stay away from these weird ones. Sometimes I mess up. Uh, and then again, the actual does not fill in the D, but again, small energetics arguments for why that is in geometry, but beyond the scope of this class.
One small thing, everyone can cover this, but why is the D block like one lower? I guess I don't know how to explain it.
Yeah, it goes back to again this whole like this ordering kind of has it, and so it's really that 4s and 3d are really close together, right? And so I think that 4s is just a little bit lower, but again you get discrepancies kind of depending on the shape, right? Because the different shapes can kind of throw the d's a little lower or the s's, but again that's like beyond the scope of this class kind of. So that's why I'm just like, just fill it in kind of as we expect it, right? Like I just expect y'all to get this order, but we don't need to get so wrapped up in like exceptions, yeah.
This might be a stupid question, but why are those two on the end of the F block colored yellow? Because it says that the ones that are yellow are D blocks.
Yeah, so that was the point that I was trying to make is like, uh, and this is like, again, kind of down the rabbit hole, but researchers have kind of felt that the characteristics of lutetium and lawrencium are better characterized as D block. But like I was explaining, well, that doesn't match with how they fill in electron configuration wise. So that's why there's all this like debate. And then right, that one has it different. So they have a dark line between lanthanum and actinium. So I would put those based off of that periodic table in the D block. But that's why there's a big discrepancy. Is like it depends on how you characterize them, what we're looking at. But again, it's kind of a moot point for this class. And so then we have neodymium. Again, doesn't have D's, but I don't expect y'all to know that. So if you put 5D1, 4F3, that's fine, right? Again, as long as you have the correct total number. And so they just kind of fill in, mainly filling up the F's. And then notice, right, this element 64 goes back to filling the D's. So again, it's just all about what's energetically favorable. That's what causes these little oddities. And then terbium does not have the D filled, but again, I don't expect y'all to know this. Just get the total number of electrons correct. So filling in, and then, and this could be the other argument for putting lutetium back at 5D1. Again, it doesn't always make sense, but lutetium now has 5D1 again, but I would still fill it as 5D1 and then 4F14, right? And that'll get you the same electron configuration. And then either way, so the most important thing to remember is to just fill in your F block, right? So I'll probably try to avoid the F block itself, but fair game would be like tungsten, for instance, right? So I might ask you the electron configuration of tungsten. So let's practice that. But again, tungsten, we have to start back at xenon for our noble gas shorthand. And then I would say, don't forget the F block. All these numbers shoved in there. So yeah, so write tungsten's electron configuration. Well, remember, it's 14 to fill it up completely. So that's kind of my point with tungsten. It's like once we move past the F block, right, we just need to worry about filling it in completely, right? We don't have to stress so much about the order like we were getting with the 5D1, right? Once we just kind of have moved past it. Let's see. So looking at tungsten, so we have xenon, and then so 6S, I'm looking in the chat too, because there's an answer posted. But right, just kind of following along, and let's think about where we're starting from. So xenon. And again, we'll sanity check ourselves. Oops, I didn't pull up. Let me get my calculator going.
So everything after hafnium or hafnium,
Yeah, so hafnium,
14.
well, for the F block, right? So hafnium is 5D2. But yeah, anything, as long as we filled in the F block, so that should be 4F14, right? So hafnium would be xenon, 6S2, 4F14, 5D2. But okay, so then we were at tungsten. So that would be 5D1, 2, 3, 4, which is what the chat says, right? So starting from xenon, so xenon, 6S2, then go on, fill in the F block, back to our D's, so D1, 2, 3, 4. Oh, sorry, 5D4. Question?
I thought that is it lanthanum was supposed to be 5D1, so would we just kind of ignore it?
Well, you fill it in, right? So it's 5D1, but if you're going strictly in order, it'd be 5D1, 4F14, but then once you go back to hafnium, you're back filling the 5s, right?
Oh,
So
okay.
that's why I'm like, just fill in the 14 and then you can finish counting your D's of 1, 2, 3, 4 there. And then again, right, sanity check yourself. Once I pull up the calculator. I mean, we could do mental math, but. So we started, so we said xenon is 54. So 54 plus, and then again, I'm just adding my superscripts to double check my electron count for my neutral. So plus 2 plus 14 plus 4. So then that gives me 74, which that should match, right? So 74 is tungsten. And so that's appropriate for, again, neutral tungsten, right? With the same number of electrons as protons. Does that make sense for tungsten? Again, I don't want to get too wrapped up in like the F block because there's too many oddities. And so then, right, we can just keep along. So I'll kind of try to mark this. So 5D4, 5D5, 6, 7, 8, 9, 10, right? So now again, another filled row. And now thallium starts off 6P, right? So now we're at 6P1, 6P2, 6P3, 6P4, 6P5, 6P6 for radon. Now francium starts 7, so 7S1, radon 7S2. Now we have the same oddity issue. So I would put actinium as 61, which let's double check if that matches P table. So actinium, so it does, right? So we can look at P table. So 61. Thorium follows 62. And then, well, actually that's odd, right? 62. So again, there's a bunch of oddities. And then element 91, protactinum. That does fill as we expect, right? 61, 5F12. Uranium fills as expected, but like I said, I'll probably not, we don't want to spend too much time in there, right? Like, I want you to just kind of get the picture, but I don't want to like test you on this to the point that it stresses you out, right? Like, we're here to learn. So neptunium happens to follow that. Plutonium is weird. And again, For the most part, they follow that pattern, but not always. And then we finish, so Lawrencium, right, brings us back. So now we have a full 4F14. Now we can go back. So now we're down at these super heavy elements. And then they would fill as expected, right? So 61, 2, 3, 4. So that's what's here for Seaborgium, 1, 2, 3, 4. And then again, if we were doing these, which most of these just got a name. Well, that periodic table is pretty modern then. Sorry, I'm just comparing our versions. So let's just annotate it. So right, this would be 6P1. You can tell, right? Apparently, wherever I pulled this one is a little older, just because these are all not named yet. All right, is that? Do we feel okay on electron configuration? So yeah, now is a good time for a break. So let's take a 10-minute break. So we'll be back around 2:05 or so. I'll try to print out some extra periodic tables. Yeah. And then homework lab, make sure you grab them. If you need last week's stuff, let me know. It's just sitting in my office. I just don't like dragging all the papers around. I already have too much. And then, yeah, turn in everything. I apologize for being behind. Like I said, I will work on grading hopefully today. But yeah, let's take a quick break. All right, any questions come up during the break or anything? So let's just finish off with periodic trends. So I have our table out. And so let's talk about size. And so what happens to our atom? Let's start easy. What happens to our size generally as we go down the periodic table? Yeah, it increases, right? Excellent. And hopefully that's again why we spent so much time with this electron configuration, is that these numbers are emphasizing that, right? Is like we add a new onion shell, new onion shell, new onion shell. Okay. So good. So right, our radius increases going down. Oops, I lost my A. But let's start thinking about what this means, right? Again, let's think about our reactivity. And yeah, I was thinking about it. I might blow off lithium, sodium, potassium for your lab. But right, we will see that they will get more and more reactive, and that's because of that increasing radius, right? So that valence electron gets further and further out, and so you have, right, this effective nuclear charge weakens as it goes further out, as your radius increases, and so that's what causes, right, again, the increase in reactivity, because now that valence electron is more loosely bound, so it's ready to fly. And so again, we'll see this, and it'll be more impactful when I do it in person. But we'll kind of see how lithium like gently fizzes, sodium starts getting more exciting, and it makes this little ball and floats around on the surface. Potassium is pretty quick to ignite in water, or like I said, even has the potential to auto-ignite. It doesn't always auto-ignite in air, but it can happen. And then again, potassium's our limit of working in air. And then I will refer you to YouTube videos because there's way too many people who do all those things, right? Where they smash the ampules and then they all explodes. All right, so good. Increasing radius. Now, what about as we go across? What happens to our radius? And this is kind of tricky. Yeah. So it gets smaller. So why does it do that? So it gets smaller as we go across. Yeah, why? Yeah, that's basically it. So, and right, the point that we want to make, and just to clarify, is like, so let's look at boron, right? So we'll look at boron, and again, just kind of sketching it out. So we have our boron, only one electron in our P, versus let's take fluorine for our extreme examples. And so yes, just to clarify again what you were saying, so we're adding we're adding more electrons at the same distance, right? So that's where Aubrey was saying, okay, we're effectively increasing our nuclear charge then. And so, okay, we're increasing our nuclear charge, and then it's going to make it contract, because again, you're adding electrons to that same energy level. So they're all at the same radius. We're just packing them more with electrons. And then, yeah, again, it holds them tighter and tighter. Good. All right, so let's look at other general trends. So now we can look at, well, we covered metallic character. So again, on the left side of our periodic table, more metallic. And then as we go to the right, then more non-metallic or non-metal behavior. We can also get into our ionization energy. So ionization energy. But let's look at, well, what is ionization energy? So we have to first define it. So anybody know what ionization energy is at all? I don't expect y'all to know it, but
Well, I mean, ions are charged atoms, so I guess it has something to do with that.
so yeah, charged atoms. Although you did kind of have the right idea. So ionization does refer to something becoming a cation. So the process, if we were to generalize this, is, and I'm just writing M for any atom. And so this ionization energy is also measured in the gas phase. But metal plus our first ionization energy would then give us our cation plus an electron. So how easy it is to pluck off an electron. And so let's think about all these things that we said, right? Because again, let's build upon the idea, okay, well, we're putting in more electrons at that same energy level, also just getting closer to our octet rule. So what do you think happens to our ionization energy as we go across our periodic table? And you can also think about, well, who likes to make cations and then who doesn't? So what does that tell you about our trend?
Noble gases don't like to.
So yeah, noble gases or anything with a full octet. So we can say that our ionization energy increases across, right? For all those same reasons that we said, that okay, we're still adding more electrons to that same radius. So again, they're effectively being held really tightly. So it's going to be unfavorable to try to get rid of an electron from fluorine or neon, of course, right? Those are going to be incredibly unreactive. Yeah.
Why does the radius get smaller as you go across it?
So back what we had said again from that effective nuclear charge, right? So we're adding more negative electrons to the same radius, right? So that's effectively increasing how negative it is at that same distance, contracting them. But yeah, with that same logic, though, that also explains ionization energy. So again, they're being held tighter and tighter as we fill in, right, that energy level, and so that makes it unfavorable, right? So again, fluorine would not want to give up an electron, and you probably would never see like an F plus species, right? Like that would either be extremely rare or like we don't see it, especially in our 100 level Gen Chem. But then, right, thinking back to who likes to give up electrons, well, lithium, beryllium, right, those are metals. They like to give up that electron much more easily. It still takes energy, right? It still takes energy input, but it's not as high as trying to remove one from fluorine. And then what happens to our ionization energy as we go down? What do we expect? Again, just think to the same logic, right? Our increasing radius. So yes, it would decrease. So yes, decreases as it goes down. Again, for that same logic, right? Our shell is getting larger. So now it's holding on to those valence electrons weaker. So yeah, it would be easier to ionize. And then, let's see. I was just curious if I had any graphs in my notes. Nope, nothing useful. So yeah, I'll pull up, and this is kind of the common chart. So again, seeing our ionization energy with, again, our noble gases being the highest there. Good. Oops, sorry. Wrong class. And then, so our other periodic trend, here, let me make another. This is getting messy here. And so we could talk about two different things. So they're kind of interchangeable and kind of not. So we have either electron negativity or similar but different would be electron affinity. And so let's just talk about our trend. So do you guys know who the most electronegative element is? It's kind of like a fun trivia fact.
I'm guessing it's one of the noble gases.
Actually not. Usually we ignore noble gases for our electron negativity trend. So kind of cross them out because they're pretty happy. But who really wants an electron?
Like fluorine, chlorine.
Yeah.
bromine.
So yeah, exactly, right? Those halogens, so good, right? They're 7 valence electrons. And so I circled fluorine because fluorine is the most electronegative element. It's actually not not the one with the highest electron affinity, but we'll get into the difference. But yes, let's just talk about the general trend. So same thing, our electronegativity is going to increase as we go across. Again, basically saying like it really wants the electron, it's really hungry for that electron. And then same thing as we go up the periodic table, electron negativity also increases. Again, for that same logic, right? Like we're filling in these shells that are really close to the nucleus. So that makes it, again, really want those electrons. Well, now that we looked at our general trend, let me just explain the difference. We're probably not going to go over this too much in this class, again, right, 100 level class, but I at least want you to have some awareness. But electronegativity, and this is generally kind of what you're taught, I feel like, in Gen Chem. But basically, I was trying to find a chart. I'll find a chart. So we said fluorine is the most electronegative. And so the caveat of electronegativity is it measures how much an atom pulls and pulls electron density in a bond. So this is the key difference between electronegativity and electron affinity. So basically we're saying, let's just say we took HF for instance, and then you could measure the dipole moment of that. And basically they've established that, okay, fluorine is our most electronegative, and it has an electronegativity value of 4. That's not really relevant. So if I were asking you about electronegativity values, I would give you the chart with all of them. But that's just what they established, is that fluorines are most electronegative at 4. And again, it's in a bond. So then we're saying in a bond that this fluorine would have a very large electron cloud because it has pulled all the electrons towards it and then leaving hydrogen basically exposed. So that's kind of how to think about electronegativity. And I at least want to bring up electron affinity. Like I said, I don't think it's too big of a term in our 100 level class, but I at least want you to have seen it so you're not completely in the dark. And so electron affinity is now a measure of a single atom in the gas phase. And so we can write this as a reaction. So we're saying how much energy does this process take to take our metal and then add an electron to that to make our negative ion. And so again, I don't want to get too far down the rabbit hole of this in our 100 level class, but you're at least seeing kind of the differences in the measurement. And so I'll just spoil the secret here. So chlorine actually has the highest electron affinity. And so that's kind of weird, right? Because fluorine and chlorine swap. So this is due to the fact that since it's like a single atom, chlorine is slightly bigger. So since it's slightly bigger, it can stabilize that negative charge better. But again, you can just stick to the general trend, right, that we have increasing electronegativity across the periodic table and as we go up. So right, headed towards fluorine, basically. Does that kind of make sense for that one? So like I said, we'll mainly focus on electronegativity in our 100 level class, but I at least want you to have seen electron affinity. Any other questions, thoughts for now? All right, let's start peeking into chapter 3. But like I said, we'll probably go back to this chapter or rely heavily on this chapter, right, to show us what's happening. And so now we're getting into types of chemical bonds. So then we want to get into, well, how does a bond form? And so we have our compounds are composed of atoms held together by chemical bonds. And so we'll have to look into, again, what are these chemical bonds? That's what we're starting. And so they can either result from attractions or then also, right, the sharing of electrons. And so again, we'll get into that. So our ionic bonds we'll see involve the transfer of electrons, right? It's typically going to be the metal giving electrons to the non-metal, right? That's kind of already been hinted at with our little oxidation states. We're already seeing, right, like our alkali metals, okay, that was NS1, so that tends to give up one electron, right? Just kind of thinking of sodium. So sodium, right, is going to give up its electron to become sodium plus. Our group 3s kind of do that, like aluminum boron. But really thinking about our group 1 and 2 and how they're giving electrons to any of our nonmetals. So like fluorine would then be accepting of an electron. So just kind of trying to sketch this out where we're going. So plus electron, right, gives us fluoride. And then, right, we're starting to see where things are coming together, octet rule, but again, I'm moving a little fast. And then covalent, we're going to see involves the sharing of electrons. And so that's our main focus of the class. And then we have metallic bonding that's kind of thrown in there. So metallic bonding, we won't really get into. And so generally this is just overgeneralized as a sea of electrons and kind of this delocalized system, which kind of gets us into why metals are conductive and yada, yada, yada. But again, this is a way oversimplification. So you can take my 200 level chem class where we do a slightly deeper taste into this, but again, actually this is like really poorly treated by most textbooks, but anyways.
Wait, so like, what's the difference between transferring and sharing electrons?
So we'll see that as we go through, but right, if you transfer electrons, basically, like as I'm kind of showing here, our sodium will actually give up an electron, and like in this case, right, maybe give it to fluorine. So it's like, yeah, and it's a complete, yeah, complete transfer. It also results in different properties, so we'll get into that as kind of like these crystal lattice structures. So that's the other thing is like ionic compounds make these crystal lattice structures. And actually let's look at, so this is what I'm getting at, our picture here. And so when you have the ionic bonding, again, transfer of electrons, so in this case we're looking at sodium, and let's slow this down for a second, right? So let's first write your electron configuration so we can get in the right frame. So write your electron configuration for neutral sodium and neutral chlorine. So just sketch that out first. So what's sodium's electron configuration?
Any in brackets and then 3s1.
Any 3s1. Okay, perfect, right? So again, we're just kind of rebuilding, re-emphasizing 3s1, right? One valence electron. We hopefully know that from our periodic table. Again, right, like annotate your periodic table however you need. So it's like, yes, I know that. Like that's what your periodic table is for like helping you. That's not to go on another aside, but it's like I feel like that's why people hate chemistry is when they're forced to memorize the periodic table. It's like, no, that's not the point of the periodic table. The point of the periodic table is to use it, right? So put the information on there so it's like jumping and screaming at you. All right, perfect. So then what's chlorine's electron configuration? Yeah, go for it.
I put neon in brackets, and then 3s2, and then 3p5.
All right, looking good there too, right? So again, 7 valence electrons, right? Looks good. Okay, maybe at this point we can even draw our Lewis dot structures to help us, again, just kind of put everything together in our mind, what's happening. So you have sodium, and then our chlorine here. Okay, and so now they're going to react. And this would be pretty nasty, gnarly reaction, by the way, which I think is also pretty fun about chemistry, right? You take sodium metal, so obviously water reactive, right? There's no way you could try to eat sodium metal. And then you take chlorine gas, again, another super toxic compound. You mix those two together and you get table salt. I don't know. I think that's the most beautiful thing. And so, again, thinking about what's happening, and so that means our electron is going to leave from sodium, go to chlorine. So that leaves us right with sodium plus. And this could be an appropriate electron configuration, Lewis dot structure as well. I kind of wrote it too many times. And so again, we're back to our neon, so noble gas, octet rule. That we want 8 valence electrons, so going back to neon, right, it's 2s2, 2p6, so we have our second energy level filled. So again, that's why sodium wanted to get rid of this valence electron so it can go back to neon. And then chlorine, we can write out, so now it's become our negative chloride. So put a negative charge on it, and then 1, 2, 3, 4, 5, 6, 7, 8. So right, also satisfied by the octet rule. And we can write new electron configuration for chloride would be neon, 3s2, 3p6. Right, so again, both of these taking us to our noble gas configuration. And so one of the important distinctions, and what I was getting at earlier, was that crystal lattice structure, right? So now we have repeating units too, and other things to take a note at. So your radius shrinks for your cation, and then it increases, right, for your anion since you have an extra electron. Yeah. Oh, question?
Yes. I was just wondering about like the charge of the actual elements. Is it usually just told to you, or is it like usually pretty consistent?
So the charge goes back to our periodic table. Let's see. Let me copy it over. Oh, that's the wrong class. So right, it should correspond. Oops. I want to copy it, not completely. Oh, I did have notes there. My bad. So yeah, my last page is my periodic table. So again, I would annotate this. So these tend to do an oxidation state of 1 plus, right? But that goes back to the fact that they have 1 valence electron, right? So that's how we know that sodium's just going to make that 1 plus because they just had 1 electron. But again, right, write it in your periodic table so that it's screaming at you. So all our alkali metals, right, will all become this 1 plus oxidation state. Our alkaline earth will be 2 plus, right, because they have 2 valence electrons to lose. Then group 3 tends to be 3 plus, typically seen with like aluminum or gallium. And then this is where the oddity happens, kind of like the switch, I call it. And so sometimes carbon can be 4 plus or 4 minus, or it tends to make covalent compounds. And then, again, that's why it goes into weird oxidation states. And then nitrogen, or group 5, tends to be 3 minus, again, especially in ionic compounds. Group 6 is 2 minus, and then our halogens are 1 minus, right, just like we saw. So again, going back to our chloride, right, we knew that it's only going to accept 1 electron, right, because it's 7, so it's just 1 away. So it's going to accept 1 electron to become just -1. Does that make sense? And then, okay, so other important things to note. So when they made a compound, since sodium is 1 plus and chloride is -1, right, they're in this, their charges match. So that's the other thing with ionic compounds, is our charges have to balance. And so this one is pretty easy. Sodium and chloride, 1 to 1, balance it out. If we were doing, and we'll get there as we continue, but if we were to do, let's just say beryllium chloride, right, or where that came from, or sorry, let's not do beryllium. Beryllium's weird. Sorry, beryllium makes covalent compounds, but magnesium chloride is a better example. So magnesium, again, however we need to look at it, right? We can think about think about its electron configuration. So I'm just sketching out its electron configuration. So neon 3s2. So again, 2 valence electrons. So that means now it's going to lose 2. So we typically see it as magnesium 2 plus, right? Like you're never going to see magnesium 1 plus. It just doesn't happen. It's going to lose those 2. And then, right, I wrote this out already balanced, but how I got there is, of course, right, we have chlorine. Well, one of them, each one can accept 1, right? So this gets 1 electron, and oh, I need another one to make them match, right? I have to have that second electron go somewhere. But again, just balancing out our charges, right? So now I have 1 magnesium 2 plus and 2 chlorine -1s, right, to give us an overall 0 charge. But that's kind of where we're going. And so again, just to emphasize, so our ionic formula is just basically our simplest unit, right? So again, we don't have a discrete, just like 1 sodium, 1 chloride molecule, right? It's this whole compound. But then, let me see if I have these notes written. So I kind of got ahead of myself. But then, again, we're seeing kind of these properties that form. I was trying to find our properties. Well, apparently I don't have them written. But properties of ionic compounds. So our properties, so they tend to have high boiling points or melting points. And again, it's because of the stability of this repeating crystal lattice structure. They're also extremely like brittle and hard though, right? So you can imagine if you were trying to cut like a little bit of salt off, right? It'd be extremely difficult to chew, and then when it does, right, it kind of shatters. And so again, that goes back to those properties here. And blah, blah, blah. We'll come back to that. And then, so just a quick look at covalent bonding, and again, where we're going. And this is why I also get overexcited about these Lewis dot structures, is if we look at our covalent bonds, so it's showing us ice. Well, what's our Lewis dot structure of water? What is it? Or oxygen. How many valence electrons does oxygen have? You can also just give me that. 6. Excellent. So right first in the S, then. So 1, 2, 3, 4. Okay, so here's our Lewis dot structure for oxygen. And then what would hydrogen look like? So just 1. Perfect. Okay. Now this is already showing us a lot of action right here. So we have these kind of just single electrons, right? So this is implying, well, it wants to make a bond. And so that's exactly what water looks like. And again, each atom contributing 1 electron to that bond here, that covalent bond of sharing. So again, we have this sharing. And again, we'll get into these lone pairs. And that's kind of why I drew it bent. But it's because of those lone pairs occupying shape. So all these things are kind of coming out. But
This satisfies the octet rule as well.
yeah, so I won't, well, I guess we can count it out, right? So 1, 2, 3, 4, 5, 6, 7, 8 from being shared. Hydrogen gets the duet rule, right? 1, 2, 1, 2. So yes, everything should be ideally satisfied. And then the important distinction between the ionic and the covalent is the covalent is a discrete little structure, right? So you do have a discrete oxygen and 2 hydrogens bound, and your formula reflects that structure, right? Like your formula reflects that that is a discrete little molecule. And then so because of that, covalent compounds tend to have like lower melting points and boiling points, again, compared to ionic compounds. You just think about water, right? We can see it at all different stages. Many medicines, too, have really low melting points, boiling points, again, relatively speaking. So yeah, actually, I think that's what, let's do that. Because I forgot to go back to your point of like, let's kind of redo our Lewis dot structures so we're all on the same page, right? So group 1, what's its Lewis dot structure going to look like, right? NS1. So what do we say? So 1 valence, so 1 dot, right, on any side. So I'll just draw some representative examples. So group 2, what do we expect? So remember, I have particular opinions about how it should be drawn based off of this NS2 one. So where should our dots be? So 2 on one side, perfect, right? So I would do it like so. Again, you may see differences in other textbooks, but I don't like that. Unless, like I said, we're talking about something very particular, but let's not go there in this class. And then, right, group 3. Again, our 3 valence electrons, so NS2 and P1. So I'll draw aluminum. Again, 2 on one side, 1 on the other. Group 4. So remember, group 4, we mentioned carbon could be our one exception just because it tends to hybridize a lot. This goes into other oddities about carbon. So carbon is also actually smaller than we expect it to be. So that's another reason why we're carbon-based life forms. But otherwise, the rest of group 4 should look like our germanium examples. So 2 on one side, and then 1 single electron. So again, that's reflective of reactivity of those heavier group 4 analogs to carbon. which again gets into a lot of other chemistry things that are beyond this class. So group 5, representative model. So 2. So a pair, and then 1, 2, 3. And again, this has implications. So group 5 tends to make 3 bonds. And then we'll see expanded octet where it can make 5, although not nitrogen for reason of sterics. But again, that's kind of too much already that I've said. And then group 6, just to continue. And again, right, just like we saw with water. So group 6 tends to make 2 bonds. So our oxygen will bind to something. You can also have oxygen like this. So making a double bond with carbon. So that's formate. This is a simple molecule, but again, still making 2 bonds. Sorry, drawing in my electrons. Group 7. And so now group 7, oops, tends to make 1 bond. This is again kind of implying why, right? We just have one little spot. So tends to make 1 bond. And then obviously group 8. This is going to be our noble gases. And so they should all be fully satisfied and have, right, a bunch of dots all around them. Sorry, I botched neons. And then we don't typically do Lewis dot structures for transition metals. Again, that's beyond the scope of this class, and transition metals go into 18 electron rules and yada, yada, yada. So that's, again, not relevant for our class. So this is, again, right, kind of your cheat sheet for your Lewis dot structures, right? So these are your answers right here. So again, just kind of seeing those repeating patterns, right? So we're kind of, hopefully it feels a little repetitive, right? So you want it to be like honed into your brain. You're like, okay, group 1 looks like that. 1 plus oxidation state is what it's going to make. Group 2, 2 plus, right? Group 3, 3 plus, etc. All right, so let's start to get into a little bit of our naming our compounds. And so first we're just going to focus on our first category so we can see our difference. And eventually we'll get to naming these, but initially we just want to focus on metals that form only one type of ion. So again, that's going to be our group 1 and 2, and I'll put kind of 3 in there. But mainly group 1 and 2, right? So those are always the same. And like I said, we'll save this, but again, it's going to be our transition metals that tend to give us oddities. But we'll save that for a little later in this course. And so again, we want to focus on our metal where our charge is always the same. And so this is our comprehensive list here, again for our class. So we have alkali metals are always 1 plus, alkaline earth are 2 plus, and then they throw these metals in there of zinc, aluminum. This is a slightly odd one. So silver can be in different oxidation states, but for our purposes, we're always going to consider it 1 plus. So I would like star that. So silver is always 1 plus for our class. And so then how we name our compound is we just state our first compound or our cation. So we'll put it right, we name our cation and then plus our anion, but we have to change our ending to "ide." So I'll do the first one with y'all. So for this one, right, Na is sodium. So now we go sodium, then chlorine, so chloride now. So now see if you can do these next ones. I almost spoiled them. So what do we get for MgO here?
Magnesium oxide.
Magnesium oxide,
Calcium
calcium
fluoride.
fluoride, and you guys were fast on that one. Excellent. All right, so that was really good. So I know we're almost out of time. Let's just take a second to kind of look at these formulas, right? And just think about our oxidation states. So sodium and chlorine, right? So we said sodium's typically 1 plus, chloride is -1. Again, neutral compound. Magnesium and oxygen, right? Magnesium 2 plus, oxygen tends to be -2. Once again, balanced, right? Calcium is 2 plus, fluoride is -1, but then there's two of them, right? So -1 times 2 is -2. Again, neutral. This one gets a little tricky. So we have aluminum. So that's 3 plus, so 3 times 2 gives us 6 plus there. And then oxygen tends to be -2, so -2 times 3, -6 there. Again, I just want to emphasize, right, that we have the same amount of positive charge as we do negative charge. So that's what dictates, again, our balance formulas for our ionic compounds. All right, we'll probably stop there in the interest of time. You have this periodic table to kind of help you, again, with the charges, emphasizing, again, that zinc is considered just 2 plus always for our purposes. Same thing with silver. And then kind of the most common is shown, but like we said, transition metals are going to be odd and can do many oxidation states for the reasons we were talking about, those d orbitals, right? Pesky. And then these will help you with kind of the other ones. All right. As usual, I have office hours after if anyone has any questions. Otherwise, right, shoot me emails, screenshots, etc. I'll catch up on the grading and the My Open Math stuff. If you're online, I posted my email. If you want to reach out to me and connect, or I'll hang out on stream in case there are any questions. And then again, don't forget cotton clothes, cotton clothes, cotton clothes for Wednesday's lab. I'll probably make an announcement. And your pants. Don't forget pants. And shoes. Yes, yes. Pants, shoes, closed-toed shoes.